And maybe before starting, I will just introduce you. So, yeah. Hi, everyone. Today's speaker is Camilla Hansen. She's a professor at the Institute for Applied Physics at the Goethe University in Frankfurt. She works primarily on nucleosynthesis and galactic chemical evolution and the formation of heavy elements. She got her PhD from LMU in Munich, and then she did some postdocs. The first one was at Landessternwarte in Heidelberg, then Niels Bohr Institute in Denmark, then MPIA, and then Darmstadt. And so, yeah, today she will tell us about these new observations of heavy elements in old metal stars.
Thank you very much. It's very exciting to be here. It's my first time in Toronto. I hope you can all hear me without the test, so it should be good. So today I will be talking about some spectroscopic measurements that we have made and that we have then collaborated with theoreticians on to learn more about the heavy element synthesis. So what I will be talking about today is basically how and where the heavy elements formed. You may have seen this periodic table by Jennifer Johnson before, showing sort of by dominance or by fraction where the different elements come from. And I will show how we can use an observational approach to look into more details of this. I'll also show which kind of observables we have, and then finally what is the role of spectroscopy, either high or low resolution, in all of this. So the different kinds of ways that we have for tracing nucleosynthetic events are either indirectly through low mass stars, where we, indirect I mean it is not the object that produced the elements, it's just preserving and holding on to the elements, the chemical composition. There are meteoritic grains, which we can do to a very high level of precision and accuracy, even on an isotopic level. As you will see in the low mass stars, we mainly have the elemental overall abundances. And then finally, we have the direct observations, either through transient events such as kilonova or massive stars, or a number of different formation sites, such as also AGB stars. I will focus on the low mass stars today. I will just show a few examples here on strontium, one of the heavy elements that we can basically see everywhere, no matter which instrument we point at it almost, as long as it's a spectrograph, because strontium has an extremely strong line. So we can even see it directly in kilonova. Here's a study we did on the first directly detected kilonova, where you see here this is the strontium line. And the same goes for indirect measurements on metal core stars. I will go more into these diagrams, so for now I will just flash it. But this is just to show you that each dot in this diagram is a star in which we have observed the derived chemical abundance of strontium. So more details on strontium later. So these are the two ways. I will mainly focus on the indirect traces in this talk. Now, how are we doing this? How are we carrying out these analyses, and what can they actually tell us? So as you all know, we will have had a nebula from which kind of star formed, either a low mass star or a massive star. In the case of the massive stars, we know that they go supernova on a short time scale, whereas if we have low mass stars, they could turn into AGB stars, and in the AGB phase, they would eject material into the interstellar medium. Now, these will happen on different time scales, and they will also leave behind different chemical tracers. So if we are putting together, let's say, a pattern, such as you see here, then you will have the abundances on the y-axis, and you will have the atomic number shown here. And this is then the highly integrated chemical composition after we have done several loops of massive stars and of lower mass stars, mixed it all together in the interstellar medium, and later on gotten the solar system composition. And therefore, we tend to use old metal core stars, because there we have had fewer cycles. The further back we look in time, the less time we have had to have multiple events. So by using old stars, the idea is that we see cleaner traces of the nuclear processes that take place either in AGB stars or in massive supernovae or merger events, for instance. So if we have these old stars, we can use them in different kinds of ways. We can do galactic chemical evolution studies So here we have the abundance of a given element versus iron versus the metallicity. So here we have a proxy for time on the x-axis. And as you're looking towards your left, you're looking back in time. If we now have a lot of stars, we can put them together as an ensemble and study the chemical evolution of the Milky Way. Or what we can also do is we can pick a single star in the Milky Way. We can ask for a detailed follow-up. And that could be with the goal to, for instance, get detailed abundances of a large number of elements, but in just one or a few stars. And with these highly resolved high signal-to-noise spectra, we will be able to get abundances of heavy elements like thorium and uranium. Thorium is a radioactively decaying element, so we can use it as a clock, and by that we can get the age of the star. This is very approximate because it's difficult to get ages of stars. If we are now getting lots of elements, and this is what I will try to show you today, what we can do is we can plot the absolute abundance here on the y-axis, the atomic number here on the x-axis. You see the observationally derived abundances are shown here as dots, and then we can compare them to different nuclear synthetic models. In blue, you're seeing the R process here, and by comparing it to different kinds of formation sites and processes, we can see if this star was predominantly enriched by, say, the R process or the S process. Or if it goes in between, then it's clearly a mixture. So with these, and this is also, I would say here, we use these old stars because here it's more likely to get a trace of just one process. And if we have a trace of, say, one process, then we can really start learning something about the underlying physics of the R process. The R process is being one of the two main processes that form the heavy elements. I won't go into this. But here, this is really the idea. Now, I want to break down this abundance diagram. I don't know how used you are to looking at abundance diagrams, but for full disclosure, here we have the square bracket notation, which tells us the logarithm of the element in the star. This is the number of absorbers in the star that gives us the abundance. We scale that to solar and then to the metallicity. And that means that here, again, we have metallicity, or proxy for H, and the element versus iron on the y-axis. Now, to really break down these diagrams, here in 0.0, we have the sun sitting, per definition. And then, as you are looking back in time towards the Big Bang over there, you will see that your chemical concentration of the galaxy, in this case the Milky Way, is dropping as you look back in time. So the events that you see up here will be highly mixed of different kinds of formation sites and processes. So we will see ejecta from supernova type 2, core collapse supernova that explode and eject material back in the interstellar medium on a short time scale. Then we have compact mergers, such as neutron star mergers. We have the lower mass AGB stars, and we have the type 1As. And then, as we are looking further back in time, there will not have been enough time for the type 1As to eject material. So that means that we can now sort out different formation scenarios, and therefore we can understand in more detail what we're looking at. If you're looking even further back in time, the AGB stars will also not have had time to eject material. And as a goal for many observational surveys, it has been to find at the lowest metallicities the ejecta of one single supernova. So you would have a mono enrichment, your low mass star, and therefore you could say 1-to-1, whatever I see in this star was actually what happened in the event before, and therefore tell me something about the process. Now this is to show you, this is what we can do with high resolution spectroscopy of low mass stars. So this is what the observer's periodic table would look like. In blue, you will see the elements of which we can see absorption features of the element from ground-based spectroscopy. Then you will see the ones that are here colored in green. Those are the ones where the strongest absorption feature is in space. So we will typically need to go to space. But as we get to know more and more atomic physics, we also start seeing some of these from ground-based spectra. And then the ones that are highlighted in orange, or half an orange, are the ones for which we can actually derive isotopic abundance formation from the stellar spectrum. And this is the highest level of detail that we can reach. And if we have isotopic abundances, then we can compare directly 1-to-1 with the nuclear synthetic processes and the predictions from the models and our isotopically derived abundances. So what do we need? Well, we need clearly stellar spectra, we need the stellar parameters. This would be, for instance, the temperature or the gravity. We need atomic data, and we need a synthesis code, and then we can derive our abundances. We always tend to make one here without the element in, so that we really confirm that this is a clean line, so we know that everything that we measure in this line belongs to the element of interest, and not another line that lies on top and mixes into the feature that we're seeing. If it does, then we need to go and measure the abundance on another line, and then filter out what belongs to the blend. And this is just one equation that I will flash. This is the only one, I promise. But this is just to show that deriving chemical abundances is actually something we derive. We don't just observe it and read it off the spectrum. The only thing that we measure is the equivalent width, where we are measuring the integrated area of the line. Then we have here different constants that we can put together. This shows us that we are basing this on a 1D local thermodynamic equilibrium assumption. So that means we have Saha and Boltzmann to describe excitation and ionization. Then here, this is the abundance we want to derive. This gives us the oscillator strength, so the atomic data. Here we have the temperature, and the absorption coefficient depends on the gravity of the star. So this tells you that due to this expression, we actually need the stellar parameters in order to get the stellar abundances, because you see temperature and gravity enter stomach. And this is then also to show you which challenges we face when we want to derive, let's say, heavy elements in old metal core stars. So the typical way of doing this is old metal core stars are not in large numbers. They typically sit in the outer parts of the halo or inner parts of it, but they are halo stars, they're far away, which means that we do not have tons and tons of information. So in order to actually first catch these ones, low resolution studies are carried out, and we have these two tracer lines here. You see calcium H and K sitting there. If these ones are weak, then we know that this is an O star, because these calcium lines are predominantly strong in cool stars, but we also know that not a lot of the chemical cycles have taken place, and therefore we see a low fraction of calcium in these stars. So when these lines are weak, then we do follow-up at higher resolution, and ultimately at extremely high resolution here, for instance, with UVIS on the DOT, and then you can see that what was before here, just a little smudge with a few lines in, due to the resolution, we can now zoom in, and we can see that there's actually a large number of lines that we can observe and measure abundances from. And this is also to show you the difference between a solar spectrum that you see here. So we know the age of the sun, we have our definition of metallicity, and if we are then looking back at a star that is about -4 in FER age, we will look back to an age that could be 10 or more gigayears. And you already see here that the really strong magnesium lines have now become small Gaussian-shaped lines, and most of the other lines are gone. And if you look back to some of the older stars we know, you see that only the very strong lines survive, and it's getting extremely difficult to just derive a metallicity and an iron abundance in these stars. So somewhere around here, there's a sweet spot where we can still learn about the nucleosynthesis, but we are still fairly safe that we are looking far back in time and detecting few nucleosynthetic events. And here is sort of to flash like the periodic table, but now as an observers or a GCE table, what we think we know and what we definitely do not know yet. So in all of these different diagrams, you will see the observations as squares or dots or little symbols. And on top of it, you will see GCE models run with different kinds of nucleosynthesis in them. So you can sort of see there's a filtering process. S is in blue. And then if we're going towards S plus R, then we have various different kinds of suggested possible R process synthesis events, as we don't fully know exactly where the R process may occur. We know that it takes place in mergers, but we still need, as you will see, different sites and different places for the R process as well. And what you might notice here is that there are some elements like strontium, yttrium, zirconium, barium. In all of these, we have a large number of detections, because here the lines fall in a part of the spectrum around 4,500 angstrom. That makes it fairly easy and straightforward to detect these. But if you're looking here towards the really heavy elements, you will start seeing that based on theory, we can predict what it should look like, but the diagrams get almost empty. And that is because it's extremely difficult to observe these elements, because they show their main transitions in the blue. And when I say blue, I mean somewhere around 3,000 to 3,500 angstrom. So the bluer you go, the more difficult it gets. What you also notice is that when you have data, you see that there's a huge abundance spread. So here, 1 order of magnitude. So you easily spread over 3 orders of magnitude in abundance space, and the uncertainties, so you have a factor of 1,000, the uncertainties would be somewhere around factor 2 or 3. So that means that what you're seeing here is actually different nuclear synthetic events enriching the galaxy, the stars in the galaxy at different times, because the spread is way in excess of any observational uncertainty that you can think of. So with this, the idea is now that we try to go to different elements or different composition, different stars, and we will try to break down and see if we can understand which of these many formation sites or processes contributed to get a given abundance. Now, in order to do that, we need to understand a little bit about the actual nucleosynthesis that takes place. This is some stuff that you all know. So we form or we synthesize in stars up until iron. Here we reach the maximum binding energy, after which further, let's say, stellar burning would become endothermic and you wouldn't get any energy out of it. And therefore, we continue typically with neutron captures, because the neutrons have the advantage that they don't have to overcome the Coulomb barrier of these heavy nuclei that are sitting in there. So for comparison, about 35 of all heavy nuclei are formed by P captures, proton captures. Otherwise, we typically have neutron captures. Now, the neutron captures will, depending on the kind of process, will be capturing a neutron. If the neutron density is high, it will capture many neutrons, and then it will beta minus decay towards stability. By that, it's going 1 higher in atomic number. So you can zigzag your way through neutron captures, beta minus decay, neutron captures, beta minus decay. Depending on how neutron rich your environment is, you will push further away from stability. You will go into the R process. If you have fewer neutrons available, you will have an S process. And this is what you're seeing here. So it was the same principle as before. You have the number of neutrons versus the number of protons. The stable isotopes, which are typically the ones that we measure in low mass stars, you see here as black. And then you can see that there's a number of different processes here. There's almost a zoo in different colors. The main ones to take away for now is here the S process, which you can see runs very close to stability. So the S process, there are fewer neutrons available. 1 neutron will typically be captured, and it will have time to beta decay, capture beta decay. In the R process, there are so many neutrons, we have an extremely high neutron density. We are talking about something like 10 to the 20, 10 to the 24 or so neutrons per cubic density, per cubic centimeter. And you will be bombarding, which means you will push further away before you reach decay. Now, here, this is the idea that with the new facilities that are either coming or already online, like EFRIP or FAIR in Germany, in Darmstadt, we will start to be able to measure the actual process and the reactions that take place. So far, this is unexplored. We can, however, backtrace what it may look like by using stellar abundances. So, you know that from the very beginning, we have the Big Bang nucleosynthesis. Then we have the stellar nucleosynthesis up until about iron or nickel. Then we have close to stability, we have the S process, typically in AGB stars, but it could also be in massive rotating stars. And then we have the R process, which is confirmed in compact mergers such as neutron-star mergers. But as I will show you, we may need at least another formation site to explain the observations that we are seeing both at low metallicity and also at high metallicity. Oh yeah, and if we want to gain information of an element like silver, you see that we are pushing far into this unknown area, and here we will typically reach the silver isotopes through an R process event. Now, this is again just to summarize what I said. So there will be different places, different processes. In the AGB stars, it could happen that we have an S process through carbon-13 pocket reactions. We capture a neutron, and this goes all the way up until lead or bismuth. Then we have the I process, the intermediate process, the slow, the intermediate, and the rapid process, which again, we have some information on, but not fully. And you can see that we have here an increasing neutron density as you go towards your right. But we have the opposite in occurrence with time. So if you're looking backwards, then what we will see first as a heavy element production channel is typically the rapid neutron capture process, and only later on, as the AGB stars have time, we will start seeing ejecta from the S process. We also have tracer elements. Barium is predominantly produced by the S process, and europium by the R process. And what we can then do is we can compare the barium to europium ratio, and thereby get a rough idea of what is the dominant production channel that enrich the star we are looking at. And this is what we're doing. We have been doing in many different kinds of studies. So here you will see again the abundance versus the atomic number. We have a number of different stars that we now see they're all enriched in the R process. You see it comes very close to the R process, all of them. But there is a little room for wiggle, and you can see that these stars are definitely not predominantly enriched by the S process, sitting down here as the dotted line. New data have also been focusing on what actually happens in a region where we can't just explain everything by an S or an R process. So here it's broken down R in red, yellow, I, S in blue. And you can see that the pattern here with the black symbols clearly needs something different here around arsenic up until strontium or even higher. And here the I process was suggested that if we really need a third neutron capture process to explain this pattern. What we then can do is we say, now we believe we have found the process that enriched the star we are looking at. Then we can go into the physics of the processes. We can start varying different parameters that will have an effect on the pattern. And in this case, we can look at, for instance, how many neutrons do we need in order to predict. And this we do through the YE. So this is a neutron fraction. And you can see here, with different neutron fractions or different neutron exposures, we will get very different abundance patterns. And then we can start saying, okay, we now believe that we have an R process running, and this R process needs to be so-and-so neutron rich to explain the star that we're looking at. Or we could play with entropy, or we could play with neutrino exposure, and so on. So the idea is really that we find first the predominant process, and then we start looking at the physics of the process. We also see here that if we're looking at the patterns, I'll go a little bit faster here, there will be peaks. So we can also look at the elements in the peak regions, and we can look at their ratios, and we can say something about, again, this is now S or R, just like you're seeing here. Now, what is interesting is that now we have our comparison. We again want to test these stars here. They're just offset on the y-axis, so we can see them better. Here we have, again, the R process prediction from any given model. It's not the important part right now. The important part is that here we have the absolute abundance versus the atomic number. And in this panel, we have the residuals. So we have model minus observation. And you see here around the rare earth region, where we have our barium tracer and our europium tracer sitting, there's a very small difference between model and observations. However, here at the lighter part, again around strontium, yttrium, zirconium, up until silver or palladium, you start seeing that there are huge residuals. And also here at the very heavy end, we see that for the actinides, thorium and uranium, there's also a difference. And this was also telling us that for a long time, we couldn't really model the R process perfectly. So what was done was we're saying, okay, whatever we have in the sun being heavily cycled of many different processes, minus S is R. But if you think about the diagram I showed you with neutrons and protons, you saw that there was a wealth, a zoo of different processes. So this would already tell you that this is not a good assumption. Now this is definitely telling you that this is not a sufficient assumption anymore. So what we were doing was to try to filter. We now say that we need at least 2 contributions, not just one R process, one universal global R process, but we will need 2. We will not call them anything, we just need 2 contributions, and we need that at low metallicity in the early universe. We may make one that will look like these stars with a heavy pattern that looks like this, and then we make another contribution here in the blue. We have a low component and a high component. And then we took a sample of hundreds, almost 1,000 metal poor stars. We did the filtering, and for almost all of them, we needed 2 contributions. So that means that we need something extra than just one universal R process, no matter if it takes place in supernova or mergers. This was also shown earlier, but people didn't really jump at that point. So this is from 2007, from the first star study. So again, here you have the barium abundance, and here you have an average of spongiobutron zirconium, the elements that showed the residuals deviation from the model. And if we do that, you see that compared to barium, there's clearly something different going on. We need a different either formation site or maybe a different contribution in order to explain that. Otherwise, it should have been flat. And again, we're again looking here also at residuals. It's the same message that we get in both cases. So what we then did was we looked at, okay, how high, how heavy do we need this extra process for, and which kind of process would it be? So we're looking here at two elements, A and B versus B over H. We are intentionally leaving out iron, because iron could be tracing a different kind of supernova, like type 1a supernova. We do not want them in the picture. We want to keep the nuclear synthesis traces of the neutron captures as clean as possible. And if they behave like this, that means that they will grow at different rates. And in that case, we will say they are not co-produced by the same process. If, however, they grow in the same way, then a co-production would leave behind a flat trend. So we looked at silver and we compared it to barium. Silver was really poorly studied. When I started doing the study, there was about 2 handfuls of stars that had silver abundances detections in them. And you see in this case, both for the giants and for the dwarfs, there are clear, let's say, negative trends in our slopes. There are clear signs of not being co-produced. That's okay, because as I showed you in the beginning, silver was sitting in the R process region. So now we're taking our R process tracer europium, comparing silver to that, and again, you can see there are clear trends of them not being co-produced. Then we are comparing silver and palladium, neighboring elements, and now you're starting to see it's really flattening out. So here we really need a different process, and we call this weak R process or limited R process, depending on whose group you follow. But it's definitely needed to explain the production of silver and palladium. And we added more. We also added ruthenium. Now I just did absolute abundances in that paper, sorry for the lack of pedagogical plots here. But here we have absolute silver versus absolute ruthenium. And again, you see you almost have a perfect one-to-one correlation. If you're doing this with the ruthenium as well, it shows exactly the same as silver. So with this, we clearly see that we need a different channel, production, or maybe even a formation site to explain these intermediate heavy elements. And this is where we also looked at strontium. So what is strontium doing? Because what I showed you now was the largest sample so far with about 70 stars or so, but this is still low number statistics. So we now look at strontium. Strontium was one of the elements where we had lots and lots of data for. We have now cut the sample size so that they are homogeneously analyzed. If we add more or not, it still serves to show you the same. So here we have strontium versus iron. We have the metallicity. Here we're looking back in time. And what we're doing here now is we are taking a galactic chemical evolution model, and then we are putting one possible formation site in at a time. And then we're exploring how is that behaving as a function of time. And so here we are taking, let's say, the lower mass electron capture supernova and exploring these as a weak R process site. And you can see here there's a slight difference, but this is mainly in the modeling of the GCE model. Then here we are now looking at neutrino-driven winds. So here we have a specific treatment of the neutrinos in the wind coming from the supernova. And this is highly parameterized. So here we get many orders of magnitude between two different trajectories that we are having. And then finally, we are now also trying to play with a possible early S process site. So here we have fast rotating massive stars. By massive stars, I mean something more than 20 solar masses. And by fast rotating, I mean something like 0.4 or 0.5 of the breakup velocity of the star. So they really have to spin. If they do that, then depending on the exact treatment and the reactions and reaction rates, and how the neutrinos and the neutrons are behaving, you will see that you can get different ratios. Now, the exact shape of the curves are not so important, but what you will see is that all these different formation sites and their reactions leave behind different traces in the galactic chemical evolution model. So in order to really explain this huge scatter that you see in the observations, it is very likely that you need to merge all these different sites in and really try to boil down at a given metallicity what is going on here. But in order to explain that spread, we need different sites. And now it flew in, but let it be. So what we then did was, okay, we now take one of these formation sites, we take the neutrino during winds from supernovae, and then we compare it to various trajectories, various parameter space in the models. So doing this together with theoreticians. And then you see here there are sort of hashed areas. These are the ones where model and observation they agree. So you can see at this part where you're above 0.5, you're actually proton rich, and here below 0.5, you're neutron rich. So you actually can explain the strontium to yttrium abundance ratio with proton rich conditions. That is sort of okay because you can see this is really in the beginning of the heavy elements. Then you're going further, you're now doing strontium to zirconium. You can see that the regions, the parameter space that suffice to explain the observations have now shrunk considerably. And if you're pushing all the way and you say that we want the same process to explain strontium and silver, you start seeing very fine regions. You can see that we either need proton-rich conditions, or if we lay it all together, you will see that here proton-rich conditions would actually work. Or we see that here the conditions that satisfy the co-production of strontium and silver are so fine that it's actually very likely that the process is not going to be robust, but it might like jump between different conditions, and therefore we don't have one universal robust R process. We now have space for having a weak R process or an early process that will either have proton-rich or varying conditions. And therefore we now try to do a follow-up. So we really wanted to have the best possible spectra so that we could really try to follow what is going on. So we got about 100 hours of observing time with the VLT. We got high resolution, high signal to noise. And as of now, these are the elements that we have derived in these spectra. You see the spectra here, and these are the observations. These are not the theoretically predicted spectra. So I want to show you what we have learned from these. We have done the lighter elements. And here the idea was really that we use carbon to nitrogen. As you know, if we go into CN cycling, we are converting carbon to nitrogen. And that means that stellar evolution will have impacted the nucleosynthesis, the abundances that we see in the surface of the star. We do this test because some of these are quite evolved giants. So it could have been that there were some internal processes like tampered with our abundances. But as you see here, we have stars that are definitely unmixed, stars here that are definitely mixed. This is the C to N comparison. What we then do is we do the CN ratio versus one of our heavy elements, again versus hydrogen. And then you see here that no matter if we take mixed or unmixed stars, they all behave in the same way. There is no trend with the neutron capture elements. So that means that what I will show you now, this is definitely nucleosynthesis that we're looking at, and not stellar evolution effects. So what we then do is we use the barium to europium ratio that I just mentioned to you earlier. Here, models predict that below this line, we have much more europium. That means that we are R process dominated, or even pure R process down here. And up here, we have so much more barium, so then we have pure S process. You see our sample has a number of pure R, and then some mixed candidates in between. What we then did was we looked at strontium to barium versus barium to iron. It looks the same if you do hydrogen here. I just want to point that out. And you can see here that no matter if you're looking at the pure stars or the slightly nucleosynthetically mixed stars, not stellar evolution, you see that they actually follow the same trend, except from this guy. This guy is an accreted star that is definitely coming from a low mass dwarf galaxy, accreted into the halo. We did no kinematic selection in our sample. So the strontium to barium ratio actually has a lot of information to tell, both on the nucleosynthesis, but also of the true origin of the star. And what we then wanted to look at was to see, I showed you the diagram in the beginning with different onsets and different tracers. What we wanted to try was to find the onset of the S process. You know, the R process takes place first in the early universe, and at some point when the ADB stars or the massive rotating stars have had enough time to eject, the S process will be seen. What you see in all of these, where you have lanthanum to barium or samarium to barium, everything plotted with respect to barium versus barium over hydrogen, so no iron in these plots, you also see that there is a break trend here. This break trend normally comes in the GCE figures because of supernova type 1a forming iron. This is not the case here because there's no iron. The case here in this break trend in our hypothesis is that this is where the S process starts. So what we did kind of, this is low number statistics again, but we did a mean shift clustering. We didn't tell it how many clusters to find. And in all cases, it actually does R process, intermediate region, S process. So we do believe that around this time, which is about minus 2.4 in barium, and also minus 2.4 in metallicity, we may actually start seeing the S process. And this is just to flash, I think I will go fast here, just to have a little bit more time for the very last. But we have completely different chemical patterns. We have stars that look like none of the other stars that I showed you so far, and we see that because we have these high resolution eye spectra. So I also wanted to point out this star, again to show you that there's a wealth of different kinds of stars. Here, this star is what I showed you as a blue line earlier, the ones that really match the R process perfectly. These are known as R-rich stars. And then down here in blue, you see that it drops off towards the heavy elements. These are known as R process or weak R process stars. And then we see we have a funny star setting right in between here again. And it also turns out that this star is actually also a pretty star. Now, just to touch on the heaviest stuff, and to show you what we can really do with these high resolution, high signal to noise spectra, we are looking now here at the very blue. So this is 3,300 nanometers, angstrom, sorry. And due to this, we can actually resolve these little details, and we can see that here we have an osmium line, and here we have a platinum line. So we can do platinum, osmium, iridium, and hafnium. Now, unfortunately for hafnium, it falls very close to, not to say right on top of, where we have molecular NH. So this is something to keep in mind. We try to filter out what is NH and what is hafnium carefully, but there might be a little bit of a residue here. But as you can see before, there were a few stars in each of these panels, taking it from the GCE figure I showed you earlier. So we had somewhere between 5 and 10 stars in the literature. Now doing this, we are getting somewhere between 20 or 30 stars in each of the different panels. You see here color-coded the metallicity, and then we have absolute hafnium versus absolute europium. Europium again being our R process trace. Here we have a 1-to-1 ratio as a solid line, and here as a dashed line, we have the solar scale prediction. And you see here for hafnium europium, hafnium being the lightest of the elements we looked at, there's some scatter. Then we are starting to look at osmium. You can see that we are moving completely away from the 1-to-1. We have solar scale, and then something happens. Now, the same actually happens in iridium. We are moving even further away again, and there's still a tail. And the same goes down here for platinum, just with fewer stars. So we can plot this in a different way. Here, the dashed line is the solar scale predictions that we would see. And then we're seeing, as we are moving into the third R process peak, so here we should see a strong R process contamination, it's starting to behave quite differently. So now we compare it again to the nuclear synthetic predictions that we get here from our collaborators. So now we're saying, okay, now we need to figure out what is actually going on in this R process, what is driving this difference that we haven't actually seen before. So we're now trying here, we're saying, okay, we have our sample plotted. We again have our solar prediction sitting here. This is solar R, solar S. You can see that we are clumping around solar R. And then here, with the different kinds of colors, I should say, we have compact mergers, so we have neutral star mergers. We have disk contribution. We have dynamical ejecta. We have disk and wind and dynamical ejecta, yes. And then we have, as an other possible site, we have the magnetorotational driven supernova. So these are supernova that are spinning and that have an extremely strong magnetic field. Like the magnetic field is really extreme. But with that, they can produce R process material. Now, in the different kinds of symbols, we are now trying to play with a different kind of physics. So we are trying to play with different fission rates, beta decay rates. We're trying to play with different mass models, just to explore the parameter space to see which kind of different R process trace we can get. And you can see that for the stars that follow the solar path, we manage at least to branch it in. But for the stars sitting here in the tail, none of the physics that we know right now, the nuclear physics that we can put into these models, can actually explain this tail. So right now, we don't know if there is something in the nuclear physics that we don't know, or if we need a different kind of formation site. But something is definitely going on, and we need something new to be able to explain this. Then I just want to flash thorium, because this was again another part where you saw that there was not a perfect match between the main R prediction and what we're seeing. And looking at thorium, you see that this is no easy task to try to mimic this part of the line. Again, this part of the line. So if you're breaking down, this is all the atomic physics that we need to put in, and we need to set all these abundances very accurately. If we get a thorium abundance that is more uncertain than 0.1 dex, then the H goes off by more than 1 gigayear off. So then we want to have plus minus 0.1 gigayear, 2.2 dex plus minus more than 2 gigayears, and so on. So here we need to both know the atomic physics and the nuclear physics really accurately, and then we can start using thorium as an H equation. I also just want to quick flash that we have now started doing kinematics of our stars. And you saw one of them was clearly looked accreted in this strontium to barium diagram. So here we're looking at the energy diagram, and here again we're plotting a different way, but this time with different dwarf galaxies highlighted in. So we have the Gaia Enceladus, the Helmi streams, the Pointer Tumnus, and Elementus 1. And you can see that about half of the sample that was not selected kinematically actually seems to follow or to come from an accreted system. And then I don't have so much time left, but I just want to say that we can do one step better. That would be to do full 3D and NLT. What I've shown you is 1D LT. For some of these elements, it doesn't really make sense to try to go there yet because we don't have enough atomic physics. But for an element like barium, we can do this stuff. And if we're really looking carefully at the stellar surface, then we should really see that we will have rising gas cells and we will have dropping gas cells. We will have cooler regions, we will have hotter regions. And that would actually lead to an asymmetric line shape, something that we will only see if we're going really to high detail, high signal to noise, and high resolution. And then we can start providing 3D NLT corrections, and these can then be generalized to a broad span of resolutions and signal to noise ratios in any kind of spectrum. But we needed the high resolution first to develop this, then we can provide a grid, and then you can apply corrections. This is also going to say that here, these corrections can for barium be found at the QSIG infra page, and you will see here how the different line shapes are actually impacted, and show this in 1D in black versus 3D, and NLTE versus LTE in dashed result. And we can then apply the corrections. So in some cases, we will see here for iron to hydrogen and barium to iron, we have applied different corrections. And you can see that sometimes the one correction actually goes in the other direction, so they sort of cancel out. But the main takeaway here is no matter which kind of corrections we apply, the huge scatter still survives, and that means we still need different nuclear synthesis processes, different sites, in order to explain the scatter that we see. And with this, I'm coming to my summary. So I want to show you that with these kind of spectroscopy, we can do abundances of up to 70 elements. We can, from this, look at stellar evolution impact. We can look at the chemical evolution of the galaxy if we have sufficiently large samples. And we can look at the physics of the nuclear processes and really try to understand which kind of event in which the star we looked at. So in order to do this, we do need complete patterns. We need to have a mixture of elements. And we also need future follow-up instrumentation where we can look at both ground-based but also space-based spectra. And this is where I would want to make a shout out that if we don't have space, there will always remain like blocks and parts in the periodic table that we can't say anything about because we need the blue spectra from space. So thank you very much.
So I had a couple questions, a couple slides back with the scatter. There, right there, that one's fun. The forward.
This one?
Yeah. So like the green ones, there's not that many, but
no.
So are the error bars comparable to the size of the points here or not?
For the 3D NLTE, they might be a little bit smaller, but otherwise I would say that typically it's around 0.2 bags.
Okay, so you're pretty sure that the scatter is not due to the observational
Yeah.
elements.
The issue is that the 3D NLTE, the 3D models are generated in a grid, and sometimes our stars fall within the grid, and for most of the cases they fell outside the generated grid.
Are these giants or these dwarfs?
Giants.
So they'll have big convection cells.
Yeah.
And they'll have slow velocities.
Yeah.
So then go back to the previous slide. So there weren't that big, it wasn't that big of a difference, I guess.
No, it depends on, so this is, I think this was done for the sun, but sometimes these also are a bit larger and larger with decreasing metallicity. So you can end up with sufficiently large corrections at low metallicity.
Why do they get bigger differences with lower metallicity?
This all depends on the number of absorbers that you are seeing and how well you can trace your number of absorbers. So the combination of temperature and
well, you said depth gets lower, but why do the differences change then?
that would be in the NLT correction. So sometimes the NLTE correction itself follows the abundance. And as you're going towards lower metallicity, your abundances are all together getting lower.
How big the velocity shift could you get back by these NLT?
You mean in radial velocity?
Yeah.
So some of them are in the halo and are pretty fast. Some of them are more nearby. So we have everything from several hundreds to just a few kilometers per second.
So I'm saying this asymmetry. If you go to
You mean how much the center of mass will cause?
how much it would affect like velocity measurement? It's like a tenth of kilometer per second, or I think it's good to know how much the effect would be. I think you had a slide showing.
Well, it's a fraction of an angstrom. You're probably at 5,000 angstroms, so it's pretty damn small.
It's small. So that's why I'm saying you need the high resolution to see this first, because at low resolution you wouldn't see it. The low resolution would already be with the signal.
You said it was like 40,000?
Yeah, a little bit higher, and I think for the sun it might be even higher. So I don't know exactly how high.
The sun's cheating, you got 24
Yeah.
times.
Exactly. But it would be, I would say, probably a fraction of tenth to tops 1-2 kilometers or something like that.
Okay,
Tops.
I just want to point out, right, 0.1 angstrom is 26 kilometers per second at 5,000.
Sorry?
I'm saying 0.1 angstrom is 26 kilometers per second at 5,000. Right, so if it's 0.01, still it's very significant. I just want to make sure it's clear. So, sorry, I'm saying that even it's only, I don't know
But I
exactly.
mean, just looking at this, right, the tick mark there is a tenth, so the shift is like a few hundreds.
But this is here's what you should look at. So
Yeah.
Oh, there you go.
Yeah, that's the plot I was saying. So it
Yeah.
is shifted by like 1 kilometer per second.
1 to a few kilometers per second.
Yeah, that's huge. So to me, this is something big enough for medium res to do. Medium res can do like at 0.5 kilometer per second now position. And you're telling me all of my velocity could offset by like 1 kilometer per second easily. That's what I'm taking on here.
Yes, but the thing is, you're not just fitting on one line, right? So you're fitting on a number of lines, so therefore you can sort of average it out, right?
Right.
So
then-
the pointier, the narrower lines you
Yeah,
have,
that's
the better
fine.
it is.
That's actually my next question then, is that the asymmetry is always the same for a particular species? Like if all of the iron two lines will be always shifting in the same direction, or it will be different, I
Yeah,
guess.
even on this one, compare that green line to the purple line, they're opposite directions.
Yeah.
Right.
So it depends on which gas cells you're following.
And you're averaging all of those, right? Because you don't resolve the stars.
No. So in the end, all of this is averaged out, and then you have one final correction. But I'm saying if you were to develop this, you need to go to the high resolution for developing it, and then afterwards you can apply it at any resolution.
Are there any other questions?
Well, actually, is that a model or is that from the sun?
I
Because
think
you
it's
could
actually
imagine
a
it doing
model
it in the
from,
sun.
yeah. I think it's a model from the sun.
Yeah.
But this is, again, I should say, this is Andy Gallagher's work. So he's in the group, so I wanted to highlight his work, but I'm not a 3D person.
Are there any other questions? Maybe online? I have not seen any. All right. Then there are no more questions for you. Then let's thank your speaker. I wanted to tell you that Camilla will be here until Friday. She's working at AB 125 in case you want to drop by at her office and say hi, talk about science. We're gonna have dinner tonight. You can sign up in the message that I sent in the reminder of the seminar. If you want to join us. And there's also going to be some light snacks. Outside.